First, Fereshte Sedehizade. Fereshte is operations coordinator at the Berliner Wasserbetriebe. Then Babak Heydari. Babak is in the Department of Mechanical and Industrial Engineering. He's professor there at the Northeastern University. And finally, Alexander Stolz. Alexander is head of the business unit security at EMI, and he's head of the safety technology and protective structures department at our institute. Welcome to the panel. Complexity is apparently a problem for any engineering approach, and that means both for research and for application. And since we now have already a clearer image of the impact of complexity on the systems we live in, as we have just seen in the presentation of Hans Heinimann, I would like to know how you, in your personal research and application environments, deal with the problem to integrate tools that address those highly complex and interdependent systems. How you think are where possible solutions are, and where the problems on the end user side are as well, because that's what we try to connect. That's what I would call a solution. So from your widespread long-term background in risk management and in addressing a big variety of topics, Hans, could you start with this?
Well, I think the first step, and we didn't talk about that, is probably building awareness. Mm-hmm. This is my experience with, especially in the Singapore context, with government agencies, where we had the chance to design and implement a formal science policy interface, so that we not just do that on accident, but a little bit more systematically. And how to create the joint understanding that we are talking about the same problem. This is for me a big problem. It needs much, much more time than I was expecting. It needs a lot of time. You have to talk to people, a lot of interactions, and to make people aware already enables them to, in a smaller environment, to cope a little bit with some of the aspects, and also in their day-to-day work to be more aware of it. So that's, for me, one key. The rest, to be honest, I think we are at the very beginning. Very often it's a data problem. Mm-hmm. Very often it's a problem that data are classified. You don't get, for example, companies. If you come to supply chain management, companies who are competitive, they don't give you all the details of their supply chain. Mm-hmm. Banking sector is the same. It's impossible to reconstruct how banks are linked among others due to privacy constraints. You cannot exactly. This seems to me a big, big challenge.
Yeah. Babak, what's your point of view, your experience?
Yeah. So, hi everyone, and thanks for inviting me. When I saw the title of this panel, I was thinking, oh, maybe the confusion around resilience was not enough, and then we added like another concept that has a lot of controversy around it, that's complexity. So we want to put the two of them next to each other. So as Hans mentioned, it's rather than coming up with a single definition or a single, even worse than that, a formula for complexity or resilience, it's important to look at, accept the fact that these are multidimensional concepts, and accept that some of these dimensions are not necessarily aligned with each other. So something that we do that increases resilience from, for example, robustness aspect might have a negative impact on the rebound aspect of the system. And so also, so the same thing with complexity. So some of the dimensions Hans mentioned a larger number of dimensions, but I wanted to mention 3 dimensions that I look at. One is the interconnectedness, which is mainly driven by the quest for efficiency. We connect different systems together to each other to increase the efficiency of mobilization of resources, and that increases the complexity. The other one is heterogeneity, and that's more or less kind of like a consequence of the first driver. So think of multimodal transportation system. It's heterogeneous because we have connected different sorts of system. And the third one is more kind of like a decentralized decision-making scheme. So we have autonomy in various parts of the system, and the goals of those autonomous parts might not be aligned with each other. So when we're talking about each of the resilience, we need to talk about each of these drivers of complexity in a different way. For example, take interconnectedness. So interconnectedness, how does it impact resilience? Generally, as the example of the financial system shows, when we make the system more interconnected, the systemic risk will go up. But at the same time, we can actually leverage the topology, who talks to whom, who interacts with whom, to get to increase the resilience given the same density of the network. Some of my research show that one of the most important parameters in the network is the degree of the community structure, what network scientists call modularity of the network. So it turns out that we could somehow balance the efficiency and resilience trade-off by carefully designing the level of modularity in many of these network systems. So that's one of the lessons. I just wanted to point also to one factor you might have heard of, this law of requisite variety that was formulated by Russ Ashby back in the 60s as a part of the control system theory, which translating into the world of complex systems says that the complexity of the system should be elevated to the level that matches the complexity of the environment. So when we're talking about how much complexity we want to put in the system, we need to understand the complexity of the context around that system. So I'll stop here and we'll...
Okay, thank you, Babak. Now, Fereshte, concrete end-user perspective. We have complexity, we have measures for resilience, say. What do you really need, and where do you see options that can make your world supplying Berlin with water and more better working?
Yeah, it's a huge topic, and the whole time I tried to focus on my position as a water supplier. How can we improve the resilience of water supply? I tell you a story too. 10 years ago, we started with the first research work for developing sensors for detection of hazardous particle in water. So how can we detect, how can we find out very fast that the water is contaminated? So this is the first, actually the first point of, if I don't know what happened in my system, I have no idea how to react, how to respond to it. So it's the first point. Now, after 10 years, and at that time, I'm telling you, we had no idea what we don't know. We started with a point and had no idea how wide this range of resilience is. And now, after 10 years, I think I could say we know what we don't know, or what are the limits of our knowledge. So in respect of resilience and complexity of water systems they haven't been getting more complex. The connection, the connectivity to other systems, the dependency to other systems has been getting more complex. But all the water suppliers through the US, Europe, they are experts. They know how to supply safe water. Everyone opens the tap, water comes out. It's normal. But how we can monitor this system in terms of quality. 8,000 kilometers in Berlin. 8,000 kilometers is almost the distance between Berlin and New York. You have to monitor it. So we started parallel to our research for sensors to ask, okay, if we have the sensors, where to place them? And what happens if they raise an alarm? So we need simulation models to find out where this contamination goes to, and where is the source of contamination. These I need in terms of being aware. And then it ends up with resilience in terms of it's not a technical issue, it's an organizational issue. And parallel to that, how can I find, you talked about the picture of what is happening. So I have to be aware of what can happen, and I have to be prepared to have a common picture of what is happening, not only with me, but all the other stakeholders, gas, power, firefighters, police, and the others. So we gathered together and started to have a common picture. Not everyone should have their own picture, you know? So they start to have their pictures. Everyone looks at, and they go to different directions. It's not a common action. And this is what we did. And now I'm really proud to inform you that in our company, we have now set up a group, a department, which starts to identify scenarios. I can simulate them with the model, and we identify resources which we have to have ready for the time something happens. And we are in a good connection to other power, gas, and the other dependent systems.
Okay.
But the last point, awareness. I think even in Berlin, as the biggest city of Germany, we have a lack of vision, a common vision for the city. The politicians, they still don't know how to create a common vision of a resilience, a common definition of resilience. We, for us, Berlin Water, we defined resilience by 4 R's: robustness, redundancy, resourcefulness, and rapidity to mobilize these resources. These are the 4 R's, and we are happy with. But the problem is, I still don't know if politicians do know the same. Thank you.
Thank you for this note also to where we need a vision. And this must start in the society and must be furthered in the political level. Alex, you talk to urban designers, to supply chain managers, to governmental institutions being responsible for German traffic roads. What is your experience with complexity, and why do you use tools with resilience measures to address it?
Okay, so I think Hans in his talk pointed out a lot of challenges we still have to face, and on the other side, talking to these end users, and when they want to address the resilience term, they're asking for solutions, or can you guide me through this? Can you give me advice how to become more resilient? And then the question is, what kind of advice can you give them? And if you integrate, of course, the complexity of a system to it, it becomes rather more complex in answering these demands. And on the other hand, we as like engineers, so to say, have the responsibility to design the system as best as we know so far. And if we want to integrate resilience into our design, we have to somehow cope with the complexity. And you perfectly pointed out that predicting these behaviors from the past, just from empirical historical data, is more or less not possible so far. So for me, the only way straightforward to is to become better in really modeling the phenomena, to be in a position to do a lot of what-if analysis. Because if we are in the position to do a lot of what-if analysis and even take into account the black swans or the other animals you mentioned, we can have a clue about what could happen. And by doing so, we can raise awareness, and we can point out to some consequences which may not be considered so far. And just by naming these consequences, I think we can broaden the range of what the stakeholders and end users have in their mind, which I think you called the sense making, or I'm more or less like having a grasp of understanding the system, get a bit of understanding this complex system. Even we know we don't have the full understanding, so just adding a piece of a puzzle to it is quite important. So from my point of view, putting real effort on it and becoming better in that, and trying to be as efficient as possible in doing that what-if analysis is just the first step, just the first step. It's not the full solution to it, and I'm not claiming that this is like the holistic approach. But nevertheless, we have to start somewhere. And even if we want to get this whole resilience thing running, we need implementation. Yeah. And this is what I'm always being asked. So can you tell me a success story within the sector where resilience have shown added value? And therefore, we really have to find implementations and success stories for that. And I think for that, it's quite important that we start with some methods available, and therefore I think this simulation part is so much important, and we are now so powerful with that. And we have like the multi-agent models, we can combine them with geo-information models, and they provide some capabilities. Maybe we have to check carefully what they're doing, but they could be a powerful tool. And on the other hand, we have now so much data available, and with the data available, we have the new methods of which everybody's talking about, like, of course, deep learning and machine learning, artificial intelligence, where we have new kind of methods in interpreting the data and coming to maybe new conclusions out of the data, and especially in a very time-efficient way. And I think these are two important things to address to these stakeholders, to address their needs to have real implementation, even if it's on a small scale starting.
Okay, thank you, Alex. But if I may comment directly on this, if you provide that kind of solutions, Hans, is this then still a resilience business? Because Alex is now working with known on a known ground. It's not the unknown.
I think I agree that we have to start just step by step. And maybe we have also to think about interaction between science and practitioners. Because if you go the standard way, it takes 10 years unless you have this knowledge in curricula. And then it takes another 10 years unless it's used, and another 10 years unless it's implemented. And I think to find new ways how to shape this interaction. And then also one model that we had in the Risk Center in Zurich, where we had problem framing workshops with our industrial sponsors. Mm-hmm. Not talking about a certain issue, but there was a feeling there might be a problem. And listening to each other, learning to each other, and jointly frame the problem. And from there, step by step, build something up. I would warn to expect a little bit too much just from models. Because in my understanding, I saw many cases when models were used, but the users didn't understand, especially if you do complex stuff analysis. I think should only be done if you have a good understanding what it does and what it means. Just one example, betweenness centrality. Mm-hmm. This has a specific, in network theory, has a very specific meaning. It means that each pair of nodes has the same probability that there is an exchange. Mm-hmm. If you do that in a traffic network or in a water network, this assumption is probably too strong. And so an analyst has to be aware and be able to relax that and to adapt it. Yeah. And there's no single silver bullet approach, but you have always to think about the context and how to make that fit in. So I think expertise is extremely important, and jointly going forward. And this idea that one day we will have a tool and then I push the button and I will have an answer, this I would warn a little bit from an approach like that.
Fereshte, you seem to have an immediate comment on it.
Yeah, it brings me to a point, modeling, of course, in terms of understanding what happened in the system. So I talk about water distribution or water supply. If I don't have any simulation model, I don't understand what happens in the system. And when I don't understand, I can't react. So that's for sure. But one big question to you researchers, this interconnection between us is very essential. I've been working now for water supply for 30 years. Don't look at this color, this is made. But one of my experience is often researchers come to us and say, we have a solution. I hope you're lucky to have a proper problem to that. It's not the way it works. You know, otherwise you will have some solution you don't need. So this is the two behaviors. I know on the one hand, I had a lot of experience with municipalities, with suppliers, with they really don't, either they don't want or they don't know what is the essential problem of them. I know that. And I'm fighting for improving their awareness of their responsibility. They are the one who should know what is their requirement. Otherwise, you will be not able to give them the proper solution, you know. But on the other hand, I would ask you very kindly, stop thinking what they could need. Talk to them. Ask them. Bring them. You know, this is modeling, for example. Modeling is good, but it doesn't help me at all if I don't have proper data for that. I don't need a black box to put in something and it gives me an answer. It's not trustable. I need robust simulation models. If the simulation model, even it is EPANET or whatever they called, if they give me minus 200 bars pressure, yeah, it doesn't help me. It's nothing what I can use. I need solution which I can trust on. You know, data on the one hand. Me, as a decision maker, even if I have a good sense of the problem, I don't need data, I need information made of this data. Evaluating data and give me information. And this is the point what we need.
Yeah. A reoccurring problem with simulation in many ways. You mentioned a lot of it. So either the big temptation of using a model, not knowing what it really assumes and what kind of equations it contains. It's all behind a graphical user interface, not having precise data, or not being physical enough to give you reliable answers. So we have now lots of statements from out of the panel. What is opinions, comments, questions from the auditory? Ivo. Ivo Hering is a reliable question taker, even late into evening sessions. Ivo is able to dig out a few questions. Please, go ahead.
I'm very impressed by this sheer number of 40 PhD topics within 5 years. So I want to ask you the following. If you think of the decision-making, kind of which model to use or which type of simulation or approach to use, do you have a kind of best practice how to select in a given context with given end users and given type of information, lack of information, the best model to describe the problem at hand and to actually solve it? Do you have a kind of process how to arrive at the model, at the simulation, at the sense making, at the evaluation, maybe even at the optimization of problems?
Well, there's no simple answer to this relatively simple question, but let me try to say a little bit how I see it. I think the first thing is there's usually a couple of tools you have to use to solve a problem. I just give you an example on what I showed. You have, of course, nowadays GIS systems that show you the lines of roads or, let's say, the water system or whatever. But if you want to do an analysis with tools from complexity science, you have to create a mathematical graph. No GIS system nowadays directly does this. So somebody has to create a mathematical graph. You have to go into some special tools. You have to do some analysis. You have to bring it back. You have to visualize. So it's heavily context dependent. I think that's the issue. It's context dependent. Then a second thing I would like to mention, how to best transfer tools into practice. I think scientists are not in a position to design something where an end user will say, oh, that's really great what you did. But it usually needs a type of process. We made very good experience. The first step is to have a showcase, very simple showcase that you can show your possible end users what can be done, and it must make meaning to them. If they don't see the meaning behind, then it's already gone. Then the next step is usually what we did to embed a PhD student, a postdoc, for a certain time in the agency where this should be applied. Yeah. They go there, let's say 1 day a week, and then they start to work with the people, and then they realize, oh, this is not exactly what they do or what they require, should do a little bit like that. But they also learn. You get a lot of things back, and then immediately come up with a better tool. So for me, it's the process is how to put that from the scientific idea to the end user, how to do that is more important for me than just to have a list. You should first use this tool, and then choose this tool, and then do this. I think that's something that still has to be developed. Then you also ask a question about sense making. I think there we are at the very beginning, how to organize a process. And I would also like to share, a PhD student of mine explored sense-making processes in an agent-based modeling environment because it's very difficult to do experiment in a real setting. Yeah. What came out is that what we always do, either purely democratic or purely hierarchical, doesn't really work well to create the best possible meaning as fast as possible. But you have to bring in a random component. And we tried also something like modified simulated annealing. Those of you working in optimization know a little bit these heuristics, that you not only continue with the best momentaneous solution, but you sometimes continue with the worst solution. Mm-hmm. And an approach like that it performed extremely well. And this shows that we have to explore totally new ways of doing that. Mm-hmm. It's not just continuing. And it reminds me what Einstein said. You cannot solve the problems with the same pattern of reasoning with which you created them. We should have that a little bit in mind when we do that. So to really search broadly and try to find new things.
I think based on 20 years experience with modeling automotive crash with and for the related industry totally underlines and supports what you said. We need to integrate those who want to apply it with those who develop it, and the best way is to mutually exchange people in the development process. And this is an always ongoing process. You will rediscover problems you thought you solved many years ago, and the basic ones on how to use, how to apply, how to trust code. And yeah.
Sorry, I wanted to add a point related to the process and also the issue of modeling and using data. So this is the age of big data, so it's natural that we think that big data might be a solution for some of these problems, especially modeling and predicting unexpected events or enhancing resilience. I would say if you think of the data that we have in this case, the big data revolution has made our data set very fat, but is still very short. So we have a lot of features for any event that has happened. We have everything in terms of the second-by-second weather condition, the second-by-second sentiment of people, consumption patterns, et cetera, but we only have a handful of samples for those events. There's a danger here, and the risk is that's a recipe for p-hacking. That's a recipe for overfitting. So you will look into the past. It's always easy to predict the past because something will predict that event, a combination of the consumption pattern 10 days before the event plus the weather condition in the morning of 4 days before the event will predict all the past financial crisis, for example. I'm just making up an example. But that's p-hacking. That doesn't have any predictive power. And researchers are very smart in putting a story behind that narrative. So all of a sudden you have a good paper, but how useful that is going to be. So I would say our community should be very careful how we deal with big data and how we bring it into our process. The modeling work, so at least for the foreseeable future, we need to somehow deal with kind of like also bottom-up modeling in addition to just data-oriented methods. But I would say predicting what's going to happen is only one of the functions of modeling, and that's not what we are necessarily looking after. A lot of times modeling is helping us to understand the fundamental driving forces, the fundamental trade-offs. It doesn't mean that we shouldn't, as the research community, we shouldn't claim that we have a black box that you push a button and it gives you, like, predict what's going to happen. I think these are the two. Yeah.
Thank you. Yeah, Steve. Yeah.
Thank you. Clearly, one of the most data-rich opportunities to understand complex systems is when they fail. And yet, for many of these system failures, particularly like natural disasters and events on complex urban systems, we don't have a formal structure that goes and learns from those disasters. Is there a research focus that we could bring to, we know complex systems will fail. I mean, it's built into it from time to time. Why don't we build an enterprise that every time they do, we go in and figure out what the characteristics of that system were that led to those cascading failures potentially, and then ideally drive some solutions.
Who wants to answer? Alex?
Yeah, so maybe I start. So my answer is rather short. That would be, in an ideal situation, a very good approach to that. But of course, you need somebody to give you the incentive to start that overall process in the end. And it all comes down in understanding the system. When we do this process that you proposed, of course, that would be to enrich our understanding with, like, empirical data. And of course, it would be very good to start the process, but nevertheless, the question is, can we fully grasp all interaction and the fully understanding of the actual cascade which happens, because we just do a post-mortem analysis. So we just see the consequences and we may just grab singular information over time. Mm-hmm. We see that a certain element fails, but maybe we do not know for what reason it fails. What are the interlinks? So sometimes they may still be invisible. So it is also it's a starting point, but I would be a bit critical that it fully resolves the system. But of course, it's like a very positive initiative to start with.
Yeah.
Just to come back what I said, I think it's not possible to predict. Mm-hmm. But what we can do is this Dragon King approach, the tools to detect. And the very simple case, how engineering geologists are using this phenomenon to predict landslides or rockfalls. You measure the width of a crack, and you monitor that in time. And you look there, it's very simple. It's a super exponential growth. As soon as you have a super exponential growth, you can say, now it's going to happen. Mm-hmm. And there's several mechanisms that we know, but we are at the beginning, as I said. But I think that's things we can do, and in at least a considerable amount of systems, we have enough time to get prepared that something happens. Of course, there are systems where the reaction is so fast, like power systems are like that. The dynamics is so fast that you cannot watch. It's already happened. So that's a challenge per se. So on the one hand side, these extremely fast processes, and others with a little more time there, I think we have a chance.
I think that was a great question, and I think that's one of the items that I had identified as one of the future research directions for complex systems resilience, and that's going back to the question of what's the equivalent of the immune system in complex systems, right? So if you think about the immune system in living creatures, not like trees or plants do not have the immune system. So only apparently the creatures that have jaws, they are the only ones that have the immune system. And the reason is first of all, they are more complex, and secondly, because they get into more dangerous interactions, they get more injuries. So that, and I think that's a great research direction to see what's the equivalent of that system. Is it the one power of the immune system is that it actually learns from small incidents. So that's why vaccination works. So then could we use like AI, reinforcement learning, some of these multi-agent reinforcement learning, but for learning from or even creating some small failure, some small incidents, and learn how to generalize them for not preventing, but reacting or responding to larger incidents.
Mm-hmm. Thank you. Yeah.
So for my respect of physical system like water supply, so our conclusion is to monitor the system the best we could. Of course, I cannot install thousands of sensors into the system in order to understand. But what we do is we have already 360 sensors in our system and try to analyze the data and to find out what is going on into the system. So, and then learn from if something happens. What I think of, this is not only in terms of to prevent or to predict, but also to reduce the risks, so to understand what could be risk and to reduce them, because analyzing risk is not only to have the risk, but multiply them by the probability of the accuracy of this risk. So this is what we do to monitor the system the best we could.
Thank you. I have seen one more question. Yes, in the far back. Yes, the two ladies next to each other. Either one, and then the other. Is there a microphone?
Yes. May I ask, use the microphone?
Oh, okay.
Yes. Thanks very much.
Okay, go ahead.
I really enjoyed the discussion on prediction and particularly limits of prediction power, and I appreciate the prudence also in the discussion on like the limits that are there in predicting these kind of extreme events. At the same time, like from a political perspective, I feel that if we focus on what we are not able to predict, that we so to speak let the decision makers off the hook to say, okay, it's unpredictable events, even though like we have quite a lot of knowledge on actually like reasonably expectable events and where obviously they are responsible for taking countermeasures. So I wonder like how we can establish processes, even if we can't make precise point predictions like when, what will happen exactly. Nonetheless, how we can prevent and prepare for these kinds of events. Thanks.
Who feels to be asked?
I think Babak showed a little bit in this direction. Mm-hmm. I think the immune system is a very nice role model that we can take. I had a chance to listen to one of the Nobel laureates who won the Nobel Prize for the immune system. And his key message is, if you don't stimulate it all the time, mm-hmm. it loses its capability. And I think we should do the same with organizations who are responsible to cope with disruptions, to stimulate them again and again. And I think wargaming is coming back. Doing wargaming exercises with organizations to stimulate them all the time. And I think that's one ingredient. We can even think in other areas going to the cyber space. I heard an interesting discussion with some Israeli guys they said the problem with cybersecurity is we transfer concepts that worked well in the physical domain to the cyber domain and try to apply them to protect the system. But going back to the immune system, shouldn't we invent an electronic vaccination to vaccinate the internet? So if you have something and can vaccinate and it spreads, you don't have to cope with. And I think that's the whole arena of new things. You really have to think broad and totally new concepts coming in. But I personally am even a fan of the immune system as a role model. I think we could get a lot of inspirations what could be done.
Yeah. Okay. Here in the corner. Yeah.
Thank you. Ting Lin from Texas Tech. So fast forward to, say, the year 2033. That's kind of the year that right now we're writing our vision for the future for Structural Engineering Institute under ASE, American Society of Civil Engineers. So what sort of next generation breakthroughs would you envision using either AI coupled with maybe high performance computing or any type of advanced technologies to embrace the known unknowns and the unknown unknowns for the future complex system decision making?
I think Babak wants to answer.
So I think several of the things that we already mentioned, like this metaphor of immune system and integrating that with AI, that's one possible direction. I would point to another direction that I think another trend that we're seeing is the whole rise of platform-based systems and sharing economy systems. And if we think about it, they actually show a model that is extremely flexible in matching the supply and demand in a very dynamic way based on sudden changes in the environment. So think of some of the mechanism that Uber, for example, uses with surge pricing, or like Uber or pooling, or some of the, so regardless of the what our ideological stance is towards those actions they are extremely efficient in dynamically connecting supply and demand. So I was back in 2012, I was living in a 50-story high-rise next to the Hudson River, north of Hoboken. So if you, during Hurricane Sandy, most of the horrible pictures that you saw were not necessarily in Manhattan, they were from Hoboken. So I was living just a mile north of that city. And for 9 days, that 50-story, 3-building, each of them close to 500 apartments, didn't have power. So what happened was there was an instant spontaneous emergence of networks of cooperation where people volunteered to provide food and assistance to the elderly community, people who actually did not even know each other's name until the day before. So think of using kind of like equivalent of Uber platform or Airbnb, some platform-based system to connect these sorts of supply and demand. Think of the implications for the evacuation process. Think of the implication for the post-disaster response. And I think one of the direction that we should be thinking is how we can take some of the lessons that we learn from these platform-based systems into there.
Another example comes to my mind that was implemented in Japan, in Tokyo. The Japanese established a network of earthquake-safe cell phone recharging stations. But it's not mainly the purpose to recharge cell phones, but they expect that people want to recharge cell phones, and they use this as nuclei of reorganization, of social reorganization. So things like that, I think we have to think about also in a social domain that we can use. And especially, I think in Japan, many things are going on, especially at the University of Tohoku. They have about 30 professorships somewhat related to recovery, because they are aware that something could happen in Japan that nobody can imagine, so they try to push that up. So there are many interesting concepts, even in the social domain, that we can learn from.
Okay. So, in the interest of time, we have one more question, please.
Hans, is it coming through? Yeah. Hans, correct me if I'm wrong, but I think you were talking about the resilience of systems, of humans and control systems. And what does that say in the longer term about the resilience of the humans?
Well, as the problem is, the way we see resilience is a trade space, the 10 dimensions, and you have an efficiency frontier, and depending what is important, you end up somewhere else. So it's not so easy to say it's resilient or not resilient. You have to identify the trade-offs. The other thing is more and more decisions are made by machines. I think that's a reality. If you look at the number of transactions going on in the financial system automatically, and compare that to the 1960s, it probably was 100% human in the 1960s, and it's 98% now by machines by 2000 and close to 20. So in the long term, I think, for me, a big challenge is how do we bring this reality, how machines see it, and the reality how humans see it, how to fuse that. Mm-hmm. Because in this Boeing case, the automatic system doesn't trust the pilots. Yeah. That's what it is. And the pilots have no access to what the system does. Mm-hmm. And I think in the future will probably be that we have many of this type of systems that jointly create somewhat a reality, and this should hopefully somewhat increase the resilience of the system. We try in the follow-up program to do how to augment sense making with all type of data fusion and sensors that we have. That's a big project. Yeah. We believe or hope that we can contribute something in this direction. What the outcomes will be, it's always like that in research, you're never sure, but maybe 4 years from that we can tell you more about it.
Yeah. Thank you. This brings us to the end of this session. Thank you again, Hans. Thank you, Babak, Fereshte, and Alex.